Okay, so Ronak will give the last talk.
So Vishnu, the group.
Well, that's not good.
Sorry, don't run away after the talk. At 12:15, we'll have a group photo. So please stay for that.
Hello everyone, thanks for the conference, thanks for allowing me to speak. I'm going to talk about very much the same subject as Abhi did, but from a different perspective. And this is working on progress with Manish, who's a grad student at IMC. He's applying this year, so please hire him. He's very good. Okay. So, yeah. Let me start with okay. Let me start with a very basic fact about entanglement entropy, which is considered a state psi in HB1 tensor HB2. Okay, in a bipartite state. Then, what you know is that psi can always be written in a particular way. Can be written as sum over some set alpha. Okay, square root of p alpha I equals 1 to d alpha alpha I 1 tensor alpha I 2 over square root. Okay. This is known as the Schmidt decomposition. It's not the Schmidt decomposition you find in textbooks, but I've rearranged it. Okay. One way to read this statement is any bipartite entangled state is a superposition over maximally entangled state. The part here is a maximally entangled state with particular values, with particular probabilities. Okay. Now this basis can be a complicated basis. Okay. I just written alpha I comma I, but suppose you have some qubit description of your Hilbert space. This could be some horrible state in that qubit description, but there exists such a state. Okay. So writing down this sort of a fall without worrying about what the bases are, it corresponds to what I call writing down the entanglement structure of the state. The only bipartite entanglement structure is the maximally entangled state. Every bipartite entangled state has superposition over this. That's what this equation says.
So this alpha I, what is alpha index? It is I index.
So alpha is just some set which corresponds to the different okay, good. Then maybe I will give this various letters meaning of gravity and it will be easier to understand.
Because in Schmidt decomposition only two n state center, right? N from this side, n from this side.
That's right. So the Schmidt eigenvalues are square root p alpha over d alpha. Okay, but I have allowed for degeneracies in there and grouped together with the degenerate pieces.
I is the degeneracy.
Yes, I is a degeneracy. Okay. So basically, what will happen is that rho 1 looks like p alpha by d alpha 1 d alpha p alpha prime by d alpha prime 1 d alpha prime, etc. Okay. The block decomposition.
So the generic decomposition would be when all the D's are 1.
Yeah. Good. Now, the problem is, this is great. We know everything about bipartite entanglement. Another important thing is that these numbers P alpha and D alpha denote the bipartite entanglement structure, and they can also be repackaged into the Rene entropies. I give you the set of Rene entropies, you can calculate these. I give you these, you can calculate the Rene entropies. Okay? We don't have anything like this, even for 3 parties, except for 3 qubits. Okay? If I give you 3 qubits, there is no such thing you can say every state is. Okay? It's actually really bad. For further,
What exactly can you not say?
that basically here you return the state as a superposition of a particular type of state.
Cannot write a canonical form.
There is no penalty. The only thing you can write is like a 3-index waveform.
It's a matter of fixing the gate symmetry, right?
It's because it's very complicated.
It's complicated or does it exist?
The answer to that is no one knows. Maybe there is a set of canonical 3-party integral states in the world. Maybe there is not. We don't know.
So gate symmetry means the U3 gate symmetry.
Yeah, no, you 3 times U, 3 times U.
Okay. But there are two things that don't exist. First of all, no such decomposition exists. Second of all, no set of measures like the Renyi entropies, which would give you the entanglement structure exists. Okay. Abhijit and various others have been working to write down newer and newer measures, but there is no such reconstruction theorem that you have for any entropies.
But one could imagine that finitely many such measures are enough to construct the state, right? Because there is finite amount of data finally.
Yeah, but no such classification exists in.
So in the 3 queries give me thousands of measures, and then I should be able to construct that.
But one actually has to do it, right? One can imagine there exists and there exists at two different states. Will it come back or do I have to do something? Okay. So now, the hope is, okay, there's no such thing for 3-party states in general, but holographic states are special. Abhijit already emphasized for us. So maybe one can hope to go further, okay, in the case of holographic states. Oh, right, sorry. Let me first tell you what this looks like in the holographic case. In the holographic case, Akers and Rath, and also Tom Karnakarov, Barov, 2018, proved that to leading order in G Newton, everything by talk will be at leading order in G Newton. The alphas are nothing but the areas of external surfaces. Okay, A over 4 Newton. A. D alpha is like E to the A over 4 Newton. And P alpha is like a Gaussian with square root G. Okay?
So alpha is not the area, you mean alphas are different extremal surfaces or something?
No, this is different areas for different external surfaces. So a holographic state is not a single geometry.
I know, but
It is a coherent state in geometry.
like alpha is just a label, it can't be a number, the area is a number.
Alpha is a label, so for areas.
Extremal surface.
So let me just finish the answer. See, a holographic state is not a single geometry. The single geometry has huge fluctuations in extrinsic curvature. It is actually a coherent state of a geometry. So give me an extremal surface. It actually doesn't take one value, but takes like a range of values of width order square root G. So area is also a label. That's why P alpha is like this Gaussian.
The area is also a label.
Area is also a label correspond to different components of your wave function.
It's the label, okay, extremal surfaces with the same area.
The same extremal surface, but different areas. Okay? So the canonical example of this is a black hole. The log corrections come from the fact that a canonical ensemble black hole does not have a single area, but actually has a superposition of areas, has an uncertainty in area. Okay?
All this area story is classical, right, sir?
Everything I say will be a leading order in detail.
No, but why are we talking about the area itself having?
It is important. So, for example, replica symmetry breaking and so on at leading order is shown by worrying about this. Like these are first operating fluctuations. They can like enhance in certain cases.
In this Gaussian is not very deep result. This result
It's not a deep result. It's common. This is common.
It's an obvious result almost, right?
It-
You have
It is. I
Gaussian
agree.
fluctuations
It
about
is
it.
implicit in many of your people also. The difference I think that these guys did was they gave a formalism that works for all extremal surfaces, not just like black holes. Or, yeah. But yeah, I agree. This is not some major result. Okay. So today I will propose an answer for the multipartite entangled states. Okay, so in AdS3 gravity, and I really mean AdS3 gravity, I mean pure GRN with negative cosmological constants, so everything in AdS3. Multipartite entanglement structures are given by direct theory of where L is the AdS radius and G is the given constant. And SLQ plus 2R is a quantum semi-group which sounds, which is some very complicated object obviously, but for those of you who know Liouville theory, this is the thing that classifies the bootstrap of Liouville theory. Okay, but I will get to that later. Okay, so what I will do is,
So what's the, say, can you just read multiparty what? Entanglement?
the multipartite entanglement structures of AdS3 gravity are given by a theory of SLQ plus 2R. SLQ plus 2R is a quantum semi-group.
What is it? Multiparty entanglement structures means some analog of this?
Yeah, some analog of this these sorts of, these are like canonical wave functions, right? Like it, every bipartite entangled state is a superposition over these wave functions.
Yeah.
So I will write down multipartite wave functions.
What is confusing me is that this structure should be a kinematic structure because it only cares about the structure of the Hilbert space.
Indeed, and this will be the kinematic structure of gravity.
By
But,
just imposing the constraints, you mean? That's
basically, yeah. It's coming from the constraints, but I won't tell you why. But another way to think about it, which I am just starting to think about, is that it's related to the quantum error correction structure of 2D systems.
So there should be nothing dynamical about this.
There is nothing dynamical
Because
about
why it should work for gravity but shouldn't work for qubits? Or like what?
No, because
What do you mean?
I am saying that there's something special about the kinematics of gravity.
There's something special about the kinematics of that.
There's something special about the kinematics. Because it states in pure GR, which has no bulk degrees of freedom, has special energy.
So what do you mean by kinematic? It should be kinematic.
It should just be it can't depend on dynamics. It's just a structure of the Hilbert space, right? So then
No, he's talking about the vacuum state, no? I'm not
Talking about the vacuum and
I think you want to write down the form of the vacuum state.
yeah.
I
In the
think
tripartite vacuum state.
this had nothing to do with vacuum state. This was just
No,
saying
no,
all states have spin decomposition.
So the result will work for descendants of the vacuum, but I think this will also generalize in similar ways to what Abhijit was talking about. But yes, the point is that the constraints of gravity constrain the kinematics of the boundary.
Sorry, but there are two very different statements. One of them is a statement about a specific set of states, like the vacuum and its descendants.
Yeah.
The other is a statement that all states are of this form. Those
All
are very
holographic semi-classical states, which are not all states in CFT. See, a CFT is a general quantum system. It has like all sorts of entanglement structure in it. But the set of semi-classical states is much more constrained.
And okay, but if you start considering quantum fluctuations and so on, then that division becomes
It does become less this thing, but typically like the states you consider in AdS CFT, they have some parametric separation. There's the A over 4 division term, there's the bulk entanglement term, and there are times when the bulk entanglement is large, but for most cases not that. Worst case, one can say that there is a set of states for which this account is true. Okay. So, what I will do today is I will outline a gravity calculation for you, and then the answer of the gravity calculation turns out to be exactly an object called the 6J symbol of this quantum semigroup. And then I will explain what the proposal is. And notice that the title had 2 words in it. There are certain very important subtleties. So let me just tell you the subtlety right now. It will pop up every time. Alpha here is a discrete set. I wrote a sum. If it was not a discrete set, I would have trouble with normalization. areas are a continuous neighborhood. Okay? And this is related to the fact that gravity does not know about the discreteness of the CFT ingredients. And this certainty will pop up everywhere, and I need to find a better way to deal with it. But modular uncertainty, so that certainty is the reason for the two-word filter. So now let me tell you about the gravitational calculation. Reflected entropy. So I will calculate something called the reflected entropy.
So the multipartite, you mean tripartite or the higher partite also?
I will focus on tripartite, but I will also tell you what the proposal is higher partite. It will be given by networks of the sort. Cool. So again, Nicholas and Rath in 2019. Okay. They proved without they proved that definitively that holography has tripartite entanglement using this quantity called reflected entropy. Oh, sorry, reflected entropy was introduced by Datta and Faulkner. I forgot to look up the year of it. Okay. So, because this is the first sharp proof of the existence of tripartite entanglement, it's a good place to start. It's also easy to calculate. I would love to calculate ambiguous quantities, but I have no idea how to do that. So consider psi.
So when you say that they proved the reflected entropy, I mean that they proved that the tripartite state has a tripartite entanglement, just that they are saying that it's not given by pairwise entanglement.
Yeah. So what is bipartite entanglement? It says that it's not you can't be moved into a state and a state there.
Yeah.
Tripartite
That was
entanglement.
already kind of obvious from the data hanging from
Yeah, people didn't know that. People had Hendrik Hayden and others tried to argue that there was no tripartite.
Who tried to argue?
Hendrik Hayden, Maloney, and various others said there was two parties, there was four parties, there was three parties. And this case two parties. So it was not obvious, maybe it's obvious to you, but historically this is where the proof is. Okay? So now let me write this state psi in HB1 and HB2 and HB3 as sum over alpha 3 square root p alpha 3 I equals 1 to d alpha 3 and 3 over 2 tensor alpha 3 and 3 1 3 as per 2 here. Okay, it's the same decomposition, but I have used 1 and 2 as a single system. Okay, now do you define the canonical purification? Okay, you define the state square root rho 1 2.
Yes, sir. This is the question I should have asked at the beginning of our meeting.
Just give me a minute. H is 1 star, H is 2 star, which is equal to alpha 3. I just finished the definition and I'll get you. Okay. So now the point is that here I've treated 1 and 2 as a single system. So alpha 3 I 3 will be in general be some entangled state in this system, in these two systems. So you canonically purify by saying that, taking the same state and putting it as the second half instead of something in 3. Okay. So now this is called a canonical purification. It is basis independent because I use a Schmidt basis with the special features. And then there is something called the reflected entropy, which is the entanglement entropy in the canonical purification of V1 unit V1 star. Okay? So you added this 1 star and 2 star, each of these were entangled states, and then you took this part and that part and asked about the entanglement entropy of this. Okay? And this is a complicated multipartite entanglement probe, it's not a measure. But what Eckers and Rath proved was that SR12 minus I12, where I is the mutual information, equals order 1 by G Newton, implies its existence of three-party entanglement. Okay. This is not super important, but the point is that getting the reflected entropy right is a good check of your proposal for tripartite entanglement. Yeah. Good.
Sorry, this definition of three-party entanglement that is not bipartite entanglement.
Mhm.
So what is the precise definition actually? Sorry.
Good. You cannot write it as okay. If you have three systems,
Yeah.
you can imagine a system where like you have 1, 2, 3.
Yes.
You can have 1A, 1B,
Yeah.
2A, 2B. Sorry, let me write that 1B, 1C. Okay, you split 1 into 1B, 1C, 2 into 2A and 2C.
What do we have? One has been split into.
Well, just let me write one thing and you know. A bipartite entangled state is something that looks like psi 1B 2A, psi 1, psi 2, 1C, 3A, tensor psi of 2C, 3. Okay, so it's bipartite entangled on various subsystems of 1, 2, and 3. Okay, and it will be there are part of 1 which is bipartite entanglement with 2, the part of 1 which is bipartite entanglement with 3, part of 2 and 3 which are bipartite entanglement with each other, and the state looks like this.
No, I understand roughly the words that there is. Sorry, what is the precise definition? I give you a density matrix, and I give you a subsystem like A, B, C. Like, what does it mean that there is three-party entanglement which is not?
So if a state can be written like this, it is only bipartite entanglement. If it cannot, there is
Sorry,
three.
this is some specific decomposition of.
He's not quantifying it, it's just yes, no answer.
I'm not telling you what psi 1, psi 2, psi 3 are, or 1A, or what these subsystems are.
Oh, so
For any subsystem and psi 1, psi 2, psi 3,
I see. So maybe I see. So there's some division of 1 into 2 subsystems, A and B, or B and C,
yeah.
and 2 into subsystem A and C also,
Yeah, basically like.
and
yeah.
this into A and B. I see.
Yeah. In the tensor network kind of looks like,
I see. So
whereas the
there is
tensor network or a general state looks like this.
some way to divide this into subsystems that allows the state, then it's only bipartite.
Yeah.
I see.
Yeah. You could make this precise by trying to write down tasks you can do with.
This doesn't work for mixed states. Someone is only working for pure states.
Simplify it and work in endless one. That's fine. Yeah, so like a two-party mixed state is the same as a three-party pure state. Okay? So now let me tell you about the reflected entropy in gravity. So let me consider a system split into three units. V1, V2, and V3. Okay, where V3 is half of space, V1 and V2.
What do the subscripts mean? Psi 1, 1B2A means what?
So V1 is H of V1 is B12 tensor B1C.
Huh.
B2 is B2A tensor B2C.
Huh.
These are tensor factors of the corresponding input spaces.
Yes.
And these given the corresponding pairs of tensor factors.
1B2A. I see.
Yeah, so this is the diagrammatic representation of this state. These three circles are B1, B2, B3. So this is the entanglement structure. A general entanglement structure will be like this. So for example, GHZ is not like this. GHZ state cannot be written this way. Good. So now, so you have three systems, B1, B2, B3. Okay. What you do is the canonical purification is, so this is the HRT surface for B1 and B2. Okay. The canonical purification is, you cut off the top half of this picture and reflect. This reflection trick works because I took a particularly symmetric set of subregions, but a version of it works always. This was proved by Lata and Kapler in like their paper. Okay? So now there's like four regions, B1, B2, B1 star, B2. Okay? And what you care about is the reflected entropy is the area of this green surface in this reflected state. And it's clear the mutual information kind of is the difference of some combination of these three surfaces. The reflected entropy is this fourth surface. They have nothing to do with each other. That's why they differ at reading. Okay? Okay. So now let me introduce a second ingredient I will use, which is reflected.
By the way, Ronak, just a comment. I mean, in order to show that the states are not of this form, the direct product type form, you don't really need any tripartite entanglement. You just use the entanglement entropy to show this.
Yeah, so what they did was exactly this, what you just said. Right? They said, okay, consider a state is the property of this tripartite entanglement form. They also included four-party entanglement. So with that, make it some small corrections. And then they calculate reflected entropy back. You pointed out just some entanglement entropy. They calculate mutual information.
I mean the reflected entropy, you can just compute the standard entanglement entropy.
Yeah. That's why I'm focusing on it. You get a calculation of the entropy.
Yeah, not me. I'm just saying that entanglement entropy, which is simpler than reflected entropy. Right? Just do that and we talk about it.
Yes.
Not this entanglement.
What do you have to compute specifically?
Yeah, it's just the statement that the bitted picture is not valid.
So what do you have to compute in specifically? You have to compute what?
Because you have to consider 4 regions,
Huh.
and then you have to consider all this. You assume that answer, then you show the contradiction.
The answer is also 3 regions. When you take a fourth
No,
region.
you have to guess the 4th region also.
Yeah. Anyway, I guess you're just like,
Okay.
it's the same definition, like you're giving.
Yeah.
Yeah. I agree, it's much simpler than what you're writing. And the reason I pick it is because I can calculate it without much effort.
Yeah.
Otherwise, I actually do want to calculate your answer.
Yeah. Okay.
Okay, yeah. Good. So the fixed area state is a state with fixed area. Sorry for writing this, I should have cut this. So if you have a region P1, you define a projector IP1 alpha 1. Okay? So you start with a state psi, which in this case might be the vacuum, and you define a projector. Okay? This projector is not defined in the UV Hilbert space. Okay, because it's basically like projecting onto a single maximally entangled state. Okay, and as I told you, it's very hard to find these maximally entangled states in the UV Hilbert space. So you define it semi-cluster, you define it in gravity. So let me tell you what it is. So if you have size, if you have say the vacuum normalization, it is given by the sphere partition. You take a sphere, you fill it in with AdS, and you calculate the action on that quantity. Now, what you do is, so you're basically calculating Pg e to the minus IEH with the vacuum boundary conditions by side. Right? Now let me tell you how to calculate 0, pi, P1, alpha 1. What you do is, so suppose this is P1. You say that there exists some surface with the same endpoints as P1. Some surface whose area is exactly alpha. Okay? And mathematically, what you are doing is, you say, you introduce a Lagrange multiplier, plus minus I mu, A of gamma V1, minus 1. Okay? And evaluate it by Saturn. Okay, this Lagrange multiplier, and this gamma V1 is any surface that ends on, and that has the same endpoints as V1. And then the Lagrange multiplier sets the area of the surface to alpha.
Not any surface, it should be vanishing distance dimensions.
I agree there. So now we evaluate this by Saturn, right? So the mu integral, as I told you, mu EOM metric equation of motion. First of all, it tells you that gamma V1 is extreme. Okay? So, it's not quite that picture I drew. What fun.
So this fixed area, sorry, just one, before you do, this fixed area is what? You're saying it's a metric eigenstate?
It's a metric eigenstate on a 4-dimension 2 surface.
Okay, but that thing is very singular anyway, right?
It is very singular. You should think of this as like a microcanonical window, but at leading order, it's hard to put in microcanonical windows explicitly.
I mean, no, I'm not even simpler than that. If you just think of the ground state of gravity, that's not a metric eigenstate.
It is not a metric eigenstate. That's what I'm saying. So, really, you should think of this fixed area as like doing a everything makes better sense when you integrate over this alpha 1 with a microcanonical window function.
Of the area.
Yeah. But you have to do that. I haven't done it.
Okay.
But one expects the contribution of that to be subleading. Same reason that microcanonical black holes will ground in New York story works.
Or if you integrate over a reasonable space,
Yeah, exactly. At leading order, you don't see all this. At subleading orders, you start seeing. What is current in that?
I mean, isn't this the same 1 over G Newton that you wrote down at the beginning, this Gaussian fluctuation? Just the fact that the ground state itself has fluctuations which are
Yeah, the fluctuation in the ground state of an area is like square root G Newton. So the change in the fluctuation in the entropy is 1 over square root G Newton. 1 over square root G Newton, which is what you expect from thermodynamics.
Actually, just from the ground state of gravity also, maybe just
Yeah, that's what I'm saying. Like from there you can show this. Like the Renyi entropies have a particular width which tell you that the area spectrum has to have 1 over square
in the
root.
vacuum.
In the vacuum or any state field.
In any state,
Any
no
semi-
entropy.
In any semi-classical state.
No, you can take a black hole and you can give whatever variation you like to the entropy.
If you make it bigger, then the metric becomes.
You can make it microcanonical or you can make it canonical. They're both semi-classical vacuums. It's in your hand to decide the width of the.
Okay, that's true. Right? That's true. Like
So the
that's
vacuum what you're saying is.
yeah. It is at most 1 by square root d. Anything bigger, you lose semi-classicalness. Okay. Huh? Oh, I see. Okay. So the gravitational equation of motion first of all tells you that this surface has to be extremal. Second of all, it says minus sin into a plus sin. So because you are fixing area, the conical angle around the surface will not be 2 pi anymore. It won't be a smooth surface. It will be some theta 1, and minus sin will become theta 1 minus 2 pi. This is some sin of it. Okay. Okay. And so this is the prescription for what you do for a to fix an area inside a path integration. Okay. And the point is you can fix areas of as many non-intersecting surfaces as you like. Okay. If you cannot fix the area of B2, B2 star and B1, B2 simultaneously because of this crossing, but you are allowed to fix B2 and B2 star, and B1 and B1 star, and also B1, B2. Okay. This is actually also an expression of multipartite entanglement, but I won't get into it. Okay. So what else did I say? Yeah. Okay. So now let's get to the calculation. This is the fun part. Okay. So I will calculate the reflected entropy spectrum. Okay. So what I will do is I will actually calculate the eigenvalues of the density matrix rho 1 star in the reflected. Okay, so this will give you all the any reflected entropy also. Okay. So I will pick a particular situation. The calculation generalizes in particular to a larger class, but I want to simplify this. Okay, you have given B2, B3. Now, you fix the areas. I should do the different for this. Sorry. Fix the areas of these three surfaces. Okay, this is I'm fixing the area only for simplicity. In the end, you can always, it's a projector, so you can to get back the original state. You can just integrate the projector over different values of the eigenvalue, right? So I can also do that in the end. But for now, I will fix the areas. Now, what is the reflected entropy? Reflected state. Canonical predication. It looks like B1 star, B1, B2, B star. With 4 of these polygon singularities. 10 minutes. Okay. I will hurry from you. Okay? So basically all of these areas are fixed to particular values. Now I will calculate rho 1 star in this. Okay? So remember that rho, remember that now we are thinking of a bipartite integral state between 1 star and 2 star. And we know that rho 1 star becomes filter decomposition, looks like P alpha 1 star, 1 D alpha 1 star, D alpha 1 star, O plus over. So I will really only need to calculate the D alpha 1 star and P alpha 1 star spectrum. Now D alpha 1 star, as I told you, is the exponential of an area. So this guy is really anything in RMS. Okay? Modulo the fact that it has to be order G meters. Okay? So I need to only calculate P alpha. You done with me?
Sorry, you're computing the reflected entropy of just one, right?
Yeah, I want to calculate rho 1 star, all the eigenvalues.
You want to calculate all the eigenvalues?
All the eigenvalues.
Okay.
So the way I do it is, okay, eigenvalues are given by P over D. D is just e to the area, so we know what D is, like I thought something mysterious. So we really only need to calculate P. Right? So what is P? Well, there's a very simple expression for this. Let me call this state.
Sorry, I got lost somewhere. Sorry, is this one of these reflected? This is just the vacuum you divided into 4 parts, or there's a one of these reflected entropy setups?
It's the canonical purification of this state.
So it's one of these reflected entropy setups.
Yeah.
So you took one prime, and then you did some canonical purification on the
I
other
took
side.
1 and 2, did canonical purification to get this 4-party state, and now I'm calculating rho 1.
Rho 100. Okay, fine. Thank you.
So, what I need to do is I need to calculate the expectation value of this project. B1 star. Sorry, my this is changed position. Sorry about that. I need to calculate this divided by that. That psi is that state, right? So let's do that calculation. Now I will need to erase the entire code.
don't you have to consider fixed area states? Why can't you do
Uh,
these?
You will see in a minute why fixed area becomes important. The fundamental answer is that if you want to calculate representation static objects, help to go to errors.
It has to do what?
Help to go to errors.
Helps to go to areas.
Errors.
Errors.
And this will be errors. Okay.
But your final statements, you are making statements about the vacuum or the fixed area?
You can integrate over these areas. See, the projector, right? So you integrate over the set of projectors, you get the value of this. So you can integrate again. Okay, it's our orthogonal projector. Okay. So now let's calculate. We have to calculate a ratio. So let me calculate psi. Okay. Psi is given by some path integral with some cosmic trace which imposes a scalar distribution. Okay. Basically, I told you how to put cosmic brains into a closed path integral. So this is really a closed path integral where things are identified by color. And also these two and these two are identified. I forgot to color them. Okay. And I'm just cutting it across the ecosymmetric slice. And you can see that this part is identified with this with that, and so on. Okay, so this is how to calculate psi. Now, let's put the, we want to calculate the numerator where we fix the n of alpha 1 star. Okay? So you take the two cut pieces I just told you, put them on the two ends. Now, the problem is that here, to put this guy, I need to put a cosmic brain like this, okay, which cannot cross this guy, right? Because this cosmic brain alpha 1 star is the area of that guy, V1 union V1. Okay. So to do that, okay, what I do is I add more Euclidean space. So I add these two tetrahedra. So this is a tetrahedron. Okay, you can see that it has four triangles. It's a hyperbolic tetrahedron. I just can't draw hyperbolas. And the outer regions are identified like this. Okay, they need to be. But now the inner regions, this is identified with this bottom face of the tetrahedron, this with the top face. Okay, similarly this guy in the bra is identified with the bottom face, this guy with the top face. And then these other two faces of the two tetrahedra have to be identified with each other. Okay? And this looks horrible, but it is a locally area solution with some cosmic brains. Okay? It's a very, very simple. But these tetrahedra are very important. What do you find then? Now notice that ket and the bra pieces are common to the numerator and the denominator. They were there in psi and also the projected term.
Why are you doing all this?
I'm calculating the numerator, the ratio. So I want to calculate psi phi psi over psi psi. Okay. So first I looked at psi psi, it had only the two end pieces, and the psi phi psi had these two tetrahedra.
So tetrahedron is like pi.
Yes, it is exactly. It is like the matrix elements of pi in some cases.
Pi is the area projected, right?
Pi is the area. This has to do with the habitable equation, the fact that it pops up. Okay. The point is that this ratio only cares about the tetrahedron. It doesn't care about what's on the alkanes. That's what I wanted to get. Turns out that this guy is e to the minus, let me write it like this, 1 over d alpha 1 to d alpha 1 star, okay, times e to the minus wall prime of the tetrahedron. So both tetrahedra are the same. And this wall prime is the volume of the tetrahedron plus some functions of the angles, of the various angles at times. Okay, I want a okay. The amazing fact is that this guy is the G Newton minus 0 limit of 6 J symbols of SLP. It was proved by Teschner and Watano. Okay, so this is a square of a 6J symbol up to some normalization.
So what are the 60 symbols of
This is the next part of it. Okay. So why should you care? What does this mean? Okay. Before getting into the main point, I will just say this fact is actually crucial to what for the volume conjecture that Vishnu mentioned. Okay. So now let me quickly tell you what a 6J symbol is. I will do it by analogy with finite groups. So, okay. So this is the proposal. So finite group G with irreps alpha. Okay, call alpha the irreps of finite group. So now I will just draw a line with an arrow and an alpha on top, then denote H alpha and tensor H alpha. Okay. This is like people who know lattice gauge theory have seen this. But each end of the line has either H alpha or H alpha. And if I join two guys, alpha, alpha, the state here, 0 minutes, okay, and be just 2-3 minutes. The lights went off, etc. The state here is the singlet in H alpha tensor H alpha star is the conjugative. Okay, so when I join two lines, it means that there is a singlet constraint. Okay. Now, imagine a state, and further, if I put a little circle here, that means that there is some fixed state in that little space, which I don't care. Okay, so let me just, these are factor. There is no entanglement from these two circles. All the entanglement between these two lines is coming from the singlet image. Now, a tripartite state will look like this. Alpha 1, alpha 2, and again, here is a singlet. Okay, what is a singlet? A singlet is given by the 3 J symbols. Alpha 1, alpha 2, alpha 3, I1, I2. I think I should. All of you have seen this in angular momentum. These 3 J symbols are related to Klebs-Jordan coefficients by some phases. Okay? Okay. So this is a tripartite state. So now let's do canonical purification of the state. Because see, this picture here actually denotes a state in the universe.
So is this correspond to some pattern of moving of tetrahedron?
Huh?
This moving of
The
tetrahedron?
tetrahedron will come in a minute. That's what tetrahedron means. Okay. The way you should think about this picture. Okay, let me just tell you how to think about this picture. Think about this picture. As each, what is it? That's not it. Each link corresponds like dual to an RT surface. So this is a 3-party. Okay. Now, to do a canonical purification, what you would do is you would cut this link in half and just reflect the diagram. Alpha 1, alpha 2, alpha 3, alpha 1. The arrows are a bit all over the place. I don't know. Okay. Okay? You reflect the diagram. This is your reflector. this is root. So then this is root 20. Now, in the separated state, you want to calculate the entanglement entropy of one union one star. How do you do that? Okay. Well, you notice that this guy is given by a sum over alpha 1 1 star with the same labels on the. I have not rotated the diagram, so this is 1 1 star, 2 star, times what is known as 666. Alpha 1, alpha 2, alpha 1 star, alpha 1 2, again alpha 3, alpha 1 star. So 67, this is what this is really saying is that this is an identity, a quadratic identity between self-code and matrix. There's two previous symbols here, there's two previous symbols here. This is a quadratic identity. In CFT, there's also this bootstrap condition of Liouville symmetry. In terms of all of the structure I just mentioned, and basically this can also be drawn as a tetrahedron, which I won't try to draw. 60 symbols are not okay. All of this structure I just told you generalizes from finite group to this horrible object called SLQ plus 2R, which I will not tell you anything about because I don't have time. But we know one certain Krishna actually wrote down the 6J symbols when solving Liouville theory. And Vartanov and Teschner took the G Newton going to zero limit, and you get exactly the volume of the tetrahedron.
So the 6J symbols depend on some reference on these alpha 1, alpha 2, alpha 3.
Exactly. These alphas are exactly the areas of the outermost areas of various integers.
So here these are labels of some operators.
Good. In Liouville, they are labels of operators.
Yes.
But these alphas are in the particular set of operators which are particular label set which are states in Liouville theory but not operating in Liouville.
They are labels of representations.
Yeah.
So this SL2Q that you didn't tell us about the areas are representations of that?
Yeah, so the set of errors that pop up are correspond to the real line. Okay, and basically the top half of the real line is area, and the bottom half is like the same thing with orientation reversal. Yeah, so basically, yes, the alphas are the areas. So this is how you think about it like this. So you really think about this picture.
Sorry, and in this figure, what is this pi or that you've written or whatever it is?
1 second. The pi is the thing that now you rewrite this guy in this basis. Okay, it's a different basis for the Hilbert space. And the pi projects onto this particular diagram.
No, in the figure. In the figure, what is the volume we're computing? Can you remind me?
It's the volume it's twice the volume of this tetrahedron.
I see.
These two tetrahedron to reverse form pi is codimension 0 because of Hamilton interstate. And that's the guy that is the expectation.
How do you know this is and this is somewhat true in the vacuum when you compute this?
This is the vacuum with fixed areas projectors, and you should generalize to a whole bunch of semi-classical states.
Why should it generalize? Maybe it's just an accident that for the vacuum you get this relationship.
No, you can, like people have checked numerically that SL2 plus 1 does a big thing in like black holes and so on.
But what is the physics of this fact that this is a 6J symbol?
The physics of the fact, good. I don't know, that is work in progress, or work not yet begun. Okay. I believe I can derive this from some algebraic blah blah about operator valued weights, but I haven't done that yet. Okay. Basically, it's something about error correction and distinct to the gravitational sector.
Yes.
Okay. Doesn't matter.
So I'm not understanding. Right now you said there is a geometric configuration.
Wait, let me take this. So the result is, so this guy is the inner product between this state and that state. Okay? And the difference is that here you fixed the area of 1, 2, here you fixed the area of 1, 2. This is exactly what we wanted to calculate. Okay? It is the probability of finding alpha 1, 1 star as the area in the state over here, in the original state. And there is an exact match. Okay? So the proposal is a tripartite entanglement structure is given by this 3J symbol. Okay, in this SL2 plus 2R. And higher party entanglement structures are given by superpositions of a graph like this, which are just products of 3J symbols. Okay, what I have shown is that the proposal. Okay, oh, and another important fact is that the 3J symbols are exact in G Newton. I really mean G Newtons to zero limit with the proposal. So what I showed is that the proposal implies some answer you can get from gravity. I am not sure that gravity implies the proposal. So it's a proposal moment. There's connections to error correction, and also this actually gives you a natural way to generalize bit threads that I didn't explain, and many other things here. But I guess that's a conclusion. Yes.
So if you have four party entanglement, does this proposal imply you don't have any independent four party entanglement?
Oh no, the product of the electronic functions is not three-party entanglement, because the four-party entanglement structure would look like a sum over these guys with different alpha values. Okay, but this alpha 1, 2 is not a subspace of any of these zero spaces.
I see, but
So it's actually a genuine four-party entanglement.
But can you check that you get the right four-party entanglement, for instance, using this proposal? Like, it sounds like a very strong proposal.
Yeah, this is the first check.
Huh.
So just for context, this project began in like the beginning of December, and I found this result and I'm very excited about it. But yeah, I need to check a lot more things. So this is very preliminary.
So right now, what is the subjective probability this is true?
It's high, very high.
It's very high. Okay, but
Because the SLQ plus 2 pops up very often, and this is Liouville theory is kind of the low energy theory dual to gravity, okay, pure gravity in 3D. And this is really all about, these are really conformal blocks of Liouville theory.
based on one entanglement computation, you're saying you're guessing the structure of the whole density matrix. That's a very okay.
That's true. Indeed, that's why it is not a paper, this is like a talk in a small conference. Yeah, but I do want to, in recent work with Chris Akers and Anyway, we use structures like this to prove that there is some uniqueness in the entanglement structure, and I hope to generalize that to gravity, but that has not been done. Yeah. Okay. So the point is that you can do a gravitational calculation for the reflective entropy, and you get exactly the same answer from this proposal based on this quantum Soni group. So I suspect that the multipartite entanglement structure is given by Clef-Jordan Cauchy's quantum Soni.
Last questions?
Just remind the formula for Q in terms of the calculation constant.
Good. Q is Q is e to the pi by b squared, and b is b squared is 4g Newton by L. So this is e to the plus pi.
But then you're taking, in the limit, you're just taking the Q to 1 limits.
But there is a non-trivial piece. Actually, what you have to do is it's a bit. This alpha is also scaled with b. Okay, so there's a non-trivial limit even at b.
Oh, so some things cancel each other.
Yeah.
Okay.
Good.
So you get something.
Yeah, these alphas are like a over 4 G Newton, as I mentioned earlier. So it's kind of like there's a G Newton even in the arguments. So like there are cancellations.
Okay, so you get nothing more than just SU2. I mean a SL2.
Yeah.
Representation.
In JT gravity, you get exactly SL2 plus. And JT gravity is also has a similar structure. But in this case, I think the Q definition.
So I understand that you compute the inner product of one fixed area state, where you're fixing this, and this one with the instead of horizontal wall, you fix the vertical. Inner product of that and the suggestion of that thing.
Yeah.
Okay, so and that also informs you about the structure of the state.
Yeah. Like, see, the point is, so there are a whole bunch of theorems in math called Tanaka prime dualities. will say that you can reconstruct the group from basically the 6 symbols and the dimensions, okay, and the symbols. And the point is that that also generalizes to the semi-simple weak-form algebras, which are called Lagrangian models of the literature. This is not a semi-simple weak-form algebra. This is more general. So I don't know that generalizes to this yet. So I'm thinking about it.
And this is all about fixed area states, right?
Again, you can integrate the areas in it.
Sorry?
You can integrate over areas in it. You're using fixed area states as a sort of so you know a general state of this sort. You would integrate over all 4 of these, all 5 areas, right?
With what weight does one integrate over here?
Huh?
With what weight does one integrate?
So
This is like a gravitational case, right?
It's a gravitational case.
No, but with what weight should I integrate?
Or the measure would basically be given by the expectation area of the projector in the resolution.
Yeah, what is it?
Again, by the same techniques I do. You put these molecular similarities here, you calculate the gravitational action and that gives you the. Yeah, you can do this. The point of doing this other sector stuff is to like be on a basis, a convenient basis. And then you can use some other basis, take the rest. Yeah.
It's